Hello everyone, it's Mr. Wolfe here, and in this video I'm going to be introducing waves. So what is a wave? Well, let's look at a simple example here. I know you guys have all seen different types of waves before, whether they be ocean waves, waves on a string, what have you. But let's try to analyze this a little bit more closely. So let's just say that this is a guitar string being plucked in slow motion, or maybe a jump rope that we're just kind of moving up and down, and we're seeing that wave propagate. So when we look at this, our brains automatically notice something, the fact that there's just kind of this general movement to the right? Like there's like this wavelength or these crests moving to the right? But if we actually look a little bit more closer, all right, at an individual particle, maybe the ones that are red, but you could look at the ones that are black too, all right? They'll go up and down as the wave passes, up and down. It stays in the same spot. So what's actually moving in a wave is, or being transferred or transported, it's not the mass. It's not the mass, right? That stays put. We could see that. What's being transferred here is actually energy, all right? So all waves propagate or transport energy from one point to another, all right? In this class, we're going to be dealing with mostly mechanical waves. So I want to give a more specific definition on what mechanical waves are, but first, let's just look at the parts of a wave first, all right? So a few things that we could do to more closely analyze waves is we could look at a wave's velocity. So this is the speed at which a wave, usually following a crest, passes. So if I go back here, let's just follow this crest, right? That's the speed of the wave. All right, and we're going to measure it just like we measure the motion of an actual object. All right, we're going to measure the motion of this energy here with the units meters per second. All right, the next part of a wave that we could look at is the wavelength, all right? So the wavelength is just going to be the distance between identical parts of a wave. So it could be crest to crest right here. These are two crests. It could be, these are identical parts of the wave. So notice how there's like this midline here and it goes up here. The next time it goes up right past the midline is right here. So that would be a wavelength. Or we could go from trough to trough. Usually trough to trough and crest to crest is what most people look at because it's just a little bit easier to see that those points, all right? And then we could also look at frequency. So frequency is how many times crests pass a given point per second, all right? So what I could do is, and we're going to measure that in cycles per second. So how many wave crests pass, or parts of a wave pass per second. But usually when we actually measure it, yes, the units are cycles per second, but it's going to be in hertz, all right? Just kind of like the current is coulombs per second, but we measure current in amps. All right, so I want to show an example of frequency actually over here. Let's go back to our image right here. I got my timer and I'm going to click start, and here's my cursor. I'm going to see how many wave crests pass my cursor, all right, in 10 seconds. So let's do now. So 1, 2, 3. That looks like, I think it was 3 or 4. I had difficulty looking back and forth. Let's just say it was 4, all right, after 10 seconds. All right, so that's telling me if I go back here for my units that my frequency was 4 cycles over 10 seconds. We usually measure frequency if it's in hertz. That denominator is always a constant 1 second. So if I wanted to make the denominator instead of 10 seconds 1 second, 4 over 10 is 0.4 cycles per second. So about a 4/10 of a wave pass every second. In other words, I would say that's 0.4 hertz, all right? So the more waves that pass, the higher the frequency, or the more frequently they pass, higher frequency, the less frequent, lower frequency. All right, the last aspect we're gonna look at here is gonna be the amplitude. So the amplitude is the distance from the crest or trough to the midline. Remember, this is the trough, this is the crest. So the amplitude is the distance from the top of the crest to the midline, or the bottom of the trough to the midline. That's the amplitude. It's essentially the height of your wave, and we're going to measure that in meters too. All right. So like we said, all waves propagate energy from one point to another. Mechanical waves are going to transport energy from one point to another across a medium. So that's what makes a mechanical wave is that wave, and most waves are mechanical waves, that wave is traveling across a medium. Light would not be an example of a mechanical wave. It could travel through space where there's no medium. So what is a medium? It's the type or the quality of a substance that a wave moves through, right? But a wave has to move through something. Like that's what a medium is. So an example is sound waves, right? The fact that I'm talking to you right now, what's happening is that energy from my vocal cords is getting transmitted to the microphone, And how it gets transmitted is through the air molecules, right? Or you could also transmit sound through water, or it could go through the ground as well, all right? Sometimes in old Western films, they'll put their ear to the ground, and they'll be able to hear like the hooves of horses a little bit more distinctly than just like listening through the air. So we can imagine that these would be maybe sound waves coming through a speaker, and we can see that the air molecules, for the most part, they're going back and forth, but if we look at the red dots, they're staying in one spot, but the energy is being propagated throughout. All right, so air could be an example, water, the ground, those are all different examples of mediums. But we could also look at medium in terms of the quality of the medium. All right, so for instance, if I hit a guitar string, the wave is traveling through a medium, right? Matter, in this case, the guitar string. Now, the guitar string may not change. I might still have the same string, but for anyone that's played guitar, if I just kind of tighten the strings or loosen them, it's going to change the sound of the guitar. It's going to change certain aspects of that wave. So, for instance, I could have a medium where I have a low tension string, and I could have a medium where maybe it's a high tension string, and when I pluck it, it just kind of goes back and forth real fast like that, versus a low tension string, you might actually be able to kind of see it wobble. All right. Here's the important thing: is you could change the medium without like actually changing whether I'm going from like air to water. I could just change the quality of that substance as well. All right. So these are all things that that waves could travel through. All right. Now, going back to light, light could travel through empty space. It does not need matter or a medium to travel through. So that would not be an example of a mechanical wave. All right. Now, sound does need something to travel through. So if you were ever, let's say, just outside in space, disregarding all the other factors that would kill you, and you tried to say something, no sound would be propagated because there's just no matter to propagate that sound. All right. Thanks for watching, everyone.